Hello there. In this video we're going to introduce a basic application of rational functions. Remember that a function f of x is said to be a rational function if it is the quotient of two polynomials p and q. And here of course q of x cannot be equal to 0 so that it is defined. So remember that rational functions do have horizontal asymptotes, or it may have slant asymptotes, and it will have vertical asymptotes when this polynomial q is equal to 0. So we're going to be looking at applications for rational functions when we want to evaluate this function f at extremely large positive or extremely large negative numbers, and we're going to briefly introduce an idea that is commonly referred to as an asymptotic, or just in general asymptotics. Alright, so before we actually get into a semi-rigorous discussion of asymptotics, I just want to briefly review just a couple concepts associated to rational functions, and I'm going to illustrate these basics with an example. So let us assume we have a rational function f of x, which is defined to be equal to x squared plus 5 divided by x cubed plus 8. So we're going to be looking at applications where we're going to evaluate this function f at extremely large numbers. And I don't mean like 1 million large, but I mean like really, really large, like 10 to the power of 5 million large. So what we're going to do is we're going to send x to infinity. And when you get to calculus, you're actually going to study infinite limits in a little bit more of a rigorous detail. So let us just, generalize this to sort of an intuitive approach. So when x gets really big, x squared is going to get really, really big too. But when we add 5 to a really, really, really large number, adding 5 does not really contribute anything significant. So pretty much as x goes to infinity, x squared plus 5 is pretty much equal to just x squared. Similarly, as x gets really, really big, adding 8 doesn't really add anything to the expression, at least significantly. So as x goes to infinity, x cubed plus 8 is pretty much equal to x cubed. So x squared divided by x cubed, we have 3x's on bottom, 2x's on top, which we know reduces just 1 over x. And as x goes to infinity, we know that this expression goes to 0. Now this is just a consequence of the rational asymptote theorem that we discussed in the previous video for rational functions. That is, if the degree of the top is less than the degree of the bottom, then as x goes to infinity, f of x will tend to 0. That means 0 is a horizontal asymptote for the function f. So let's just briefly formally write that down, because that's a useful property. So if f of x is equal to p of x divided by q of x, and the degree of polynomial p is less than the degree of polynomial q, then as x tends to plus or minus infinity, f of x will tend to 0. So that's an interesting property. So let's just look at an example of a consequence of that. So what we're going to do is we're going to let f of x be equal to x squared minus 5x minus 7, all divided by x to the 5th minus 2x cubed plus 2x plus 5. And what we're going to be interested in finding is we're going to say find f evaluated at 543,242. So we could plug this in to this function. Everywhere we see x, we just substitute it with our value of interest, do our order of operations, and then divide those values. But you're going to see that that's actually not quite necessary, because one can say that this number is significantly large. But of course that is a subjective statement, right? So one can say that if this number is really large, since the degree of the top, which is 2, is less than the degree of the bottom, which is 5, and notice there is some significant gap between 2 and 5, more than just 1 in the previous example. So this value should be close to 0. And one can numerically just verify this with a few examples. So let's just look at a couple. Let's just plug in 4. So if you plug in 4, you'll realize that this is approximately equal to negative 0.01. And if you plug in 10, you'll realize that this is approximately equal to 0.0004. So one can see that, even 10 is pretty much equal to 0 at least to 3 decimal places. So this is definitely going to be closer to 0 with a lot more precision to 0 than 4 and 10 are equal to. All right, so let's look at another example. So let's assume that f of x is equal to something like 4x cubed minus 2x squared plus 5, all divided by 3x cubed plus 2x squared plus 7x minus 8. So what we're going to do is we're going to do the same exact thing. So we're going to send x to infinity and see what this is approximately equal to. So notice that 4x cubed is the dominant term on the top, and 3x cubed is going to be the dominant term on the bottom. And these terms, underlined in blue, are not going to be as significant as those circled in green. So one can say that this is going to be approximately equal to the expression 4x cubed divided by 3x cubed, which is just going to be equal to 4/3 or 1.3 repeated. So you can apply this process for pretty much any type of polynomial of this structure. So if f of x is equal to p of x divided by q of x, with the degree of p equaling that of the degree of q, assuming top and bottom are polynomials, then as x tend to positive infinity or negative infinity, then f of x is going to get close to the leading coefficient of p divided by the leading coefficient of q. So in this case, that was going to be 4 divided by 3. Right? So that's very interesting. So that means 4/3 was the horizontal asymptote of the other function. So let's consider the function g of x is equal to, let's look at 3x squared minus 5x plus 2 all over 6x squared plus 5x minus 7. And what we're going to be looking at is finding g of negative 463,218. So since the top and bottom term have the same exact degree, then we can say that if this number in parentheses is significantly large, which one may be able to claim or argue, then this is going to be approximately equal to the quotient of the leading coefficients. In this case, that's going to be 3/6 or 1/2, which is 0.5. Now you can numerically test this claim to see how accurate it is. So let's look at a couple values. So let's go to negative infinity from the right hand side. So g of negative 10 is going to be equal to 0.648. If you plug in 100 negative, you're going to have that this is going to be approximately equal to 0.513. And g of negative 10,000 is going to be approximately equal to 0.5001. So yes, it does not necessarily converge or get close to 0.5 as quicker as the other example did, but it definitely does get close to 0.5 the larger and larger you get to negative 463,218. Now it's not going to be equal to 0.5, but it's going to be very, very close to this number. All right, so let's look at our next example. So let's assume we have k of x is equal to 10x cubed minus 2x squared plus 5x minus 7, all divided by 5x squared minus 2x plus 3. So remember in the last example, we noticed that If we do long division on this expression, we're going to get a quotient that is a linear function. So this is going to have what we call a slant or a linear asymptote. Slant. S-L-A-N-T. Right? Because the difference between these two is equal to 1 and the top is bigger than the bottom. So let's just quickly do that out just to see what we get. So this is going to be 5x squared minus 2x plus 3 divided into 10x cubed minus 2x squared plus 5x minus 7. Alright, so 5 times what gives us 10x cubed, so that's going to be 2x. Then I'm going to multiply that down, so that's going to give us 10x cubed minus 4x squared plus 6x. Then I'm just going to subtract that off. So I'm going to have negative 2 plus 4, that's going to be 2x squared. 5 minus 6x is going to be minus x. Then I have minus 7. Then 5 times what is going to give me 2, so that's going to give us 2/5. So 2/5 times 5 is going to give us 2x squared as designed. And 2/5 times negative 2 is going to give us minus 4/5 x. And then I'm just going to subtract that off. So I have negative 1 plus 4/5. So that's just going to give us negative 1/5 x. And then I'm just going to have this minus 7. So notice I have 5x squared here, negative 1/5 x here. So that means this is my remainder, and this is my quotient. So that means our polynomial, k of x, can be rewritten as 2x plus 2/5 plus negative, or I can actually rewrite this as minus 1/5 x minus plus 7 all over my divisor, which was 5x squared minus 2x plus 3. So what I'm going to do is I'm going to send x to infinity. So as x goes to infinity, this term here we know is going to go to 0 because the bottom term is going to get larger than the top will. So that means as x goes to infinity, k of x is going to be approximately equal to 2x plus 2/5. So this is going to be our slant asymptote, or as some people refer to as the asymptotic of kx. And you may see some people write this as k of x is asymptotic. It's like a little squiggle to 2x plus 2/5. So this is another way of saying that as x tends to infinity, kx over 2x plus 2/5 is going to get close to 1. That's an equivalent way of saying that. So let's just do a quick example. Let's find, say, k of 3,254. So by this procedure, that's just going to be just 2 times 3254 plus 0.4, which we can find to be 6508.4. And you can find the exact value, k of 3254, so this is exact. You can find the exact value to be equal to 6508.3999875 and so on. So definitely you see that these values are actually pretty close to each other. And 3,254 is not really that large compared to, what infinity. So let's just summarize this last property in the case that the degree of the top is bigger than the bottom. So if f of x is equal to p of x over q of x, with the degree of the top being bigger than the degree of the bottom, then we can perform long division and represent p of x over q of x in the form capital Q of x plus capital R of x divided by Q of x. So this is the quotient, this is the remainder, and this is the same divisor as before. And this is after long division. Long division. And of course here we have the degree of capital R will be less than the degree of little q. That is, I'm focusing on this term. So since the degree of R is less than the degree of Q, we know that capital R over Q is going to go close to 0 as x tends to plus or minus infinity. So then, as x tends to plus or minus infinity, f of x is going to tend to our quotient q of x. Or you may see this just abbreviated as f is asymptotic to q. So f is asymptotic. Now it's very important to note that asymptotics don't only apply to rational functions. This is very important. A lot of functions actually do have asymptotic expansions that are really useful for evaluating the function at really large numbers. An example of this, which we'll investigate in, say, differential or limit calculus, and that is Stirling's formula. And Stirling's formula relates the factorial when n is really large. And Stirling's formula says that n factorial is asymptotic to the expression n to the power of n multiplied by the square root of 2 pi n all divided by e to the n, where e is approximately equal to 2.71828 and so on. It's a special number like pi, and we're going to look at this number in grave detail. Right, so this is Stirling's formula. So as n gets close to infinity, how are we going to interpret this? Then n factorial is approximately equal to n to the power of n times the square root of 2 pi n all divided by e to the n. So just as an example to illustrate this idea, suppose we want to give an approximation for 500 factorial. So we know factorials do grow really, really large, really, really quickly. So 500 factorial is definitely a subjectively large number. But whatever this is going to be close to 500 to the power of 500, which we can find, multiplied by 2 times 500 times pi, which we can approximate, divided by e to the power of 500, which we can approximate, and we can approximate this quotient. Now, of course, if 500 factorial is large, its asymptotic evaluation will also be very large as well. But the pro of the asymptotic expansion is we can actually evaluate this number directly instead of finding 500 times 499 times 498 and so on, which is comparably not as effective or efficient. But this is just an application of asymptotics known as Stirling's approximation. But again, it does not only apply to rational functions, it can apply to, say, factorials or other functions as well. Hope you enjoyed.